It's 4 minutes past, right?
Yeah, I'll be just waiting for Kumarjit. I'll just start the custom streaming. Okay. I think I see Kumarjit here.
You can check with others. So I'm in no hurry. So it's fine. Sorry, I'm fine waiting. But
okay, Kumarjit, go ahead and introduce the speaker. You're muted.
First of all, apology to all of you and apology to the speaker for being late. So today I am happy to have Ognip who agreed to give a talk here. So I welcome Ognip and without any further delay, let us proceed to the talk.
oh, okay.
Sorry.
Okay. So
Ognip actually currently faculty at TIFR Bangalore, Center of Applicable Mathematics, TIFR Bangalore, and Ognip is selected as awarded INSA Young Scientist Award. So please, Ognip, you can start now. Sorry.
no, so do I start now? Then so I should share my screen. So share. So the screen is visible, no, Kumarjit?
Yes, it is visible.
Okay. So let me see if I can. So now, so is it moving? Is the screen moving?
Yeah, it's fine.
Okay, so that is also good. Okay, so I would like to thank Kumarjit for the kind invitation and also Gaurav for guiding me with further details. So I'll speak on unique continuation for in the context of parabolic equations. And this is based on a recent joint work with Nicola Garofalo and Ramesh Manna. So in the first few slides, I will bore you with a few preliminaries, most of which most of you would be familiar with, but anyway, but it would just, but nevertheless, it's very relevant. So it's good to sort of go over it. So the first thing is the notion of vanishing to infinite order. So we say that a function vanishes to infinite order if at a point x naught, if near that point it decays more than any order polynomial. So in the case when the function is okay, so now I think the below is visible. So earlier I put it a bit up. So in the case when u is smooth, this is the same as having that all the derivatives of u vanish at that point. And this is a notion, but most of the times when we are dealing with equations, the operators don't allow you to, don't admit that much of regularity, or the equation does not admit, does not enforce that much of regularity. So it's always good to have a more robust definition of vanishing to infinite order. And the one that I had over here is the one that is if it decays more than any order polynomial. So in the case when u is smooth, as I said, this is the same as having that all the derivatives of u vanish at that point. And the equivalence can be seen by writing out the Taylor expansion of u. So this is one. And the next notion is about an operator possessing the strong unique continuation property. So maybe I'll just... An operator L is said to have the strong unique continuation property, which I will abbreviate as SUCP, if non-trivial solutions to LU equals to 0 cannot vanish to infinite order at any point in the domain. So an obvious example would be the Laplacian, in which case we know that the solutions are harmonic functions and they turn out to be real analytic. And once we have that a function is real analytic, then the strong unique continuation follows, because it's not hard to see that the set of points where all the derivatives vanish is both an open and closed subset. Because at the point where all the derivatives vanish, we know that we can Taylor expand near that point, around that point, and then it has to vanish in a neighborhood. And the other and that set being closed is quite easy, right? Because it's the intersection of all. It is in the intersection of the zeros of a family of continuous functions. So then by topological considerations, it is easy to see that the zero set spreads in the connected component. Now, there is a weaker notion of weak unique continuation property, which I will abbreviate as WCP, if non-trivial solutions cannot vanish in an open subset of a connected domain. And as the name suggests, and it would be, it's quite easy to see that the strong unique continuation property, which is SUCP, is stronger, and in particular implies the weak unique continuation property. Now, before I proceed further, so if anybody has any questions, since I'm not good with checking the chats or something like that, so you feel free to interrupt and ask me questions. So that is the least I can say. So for it, now coming back to the Laplacian, here we see that in this case, the equation admits too much of regularity, and in which case the partial differential equation somewhat becomes irrelevant beyond a certain point, right? So the question of strong unique continuation is often more, or weak or unique continuation in general is often more interesting in scenarios where the operators don't admit that or don't possess that much of regularity properties or that much of hypolepticity properties. So now I will mention some known results concerning unique continuation for elliptic and parabolic equations. So for uniformly elliptic operators in divergence form, where the principal part is Lipschitz and the lower order terms are bounded, strong unique continuation was first established in the early 1960s by Aronszajn, Krzyzewski, and Sarsky using the so-called Kaleman estimates. Now the Kaleman estimates are some weighted variants of Sobolev-Poincaré type inequalities, and prototypical one looks like this. So we can think of, say, L. So L is kind of a coercive operator, right? So we can think of it as a Laplacian or say Laplace-Beltrami on a manifold, and then this can be regarded as weighted version of Sobolev-Poincaré type inequality, right? Because if you control U in terms of du, that is a Poincaré inequality, and then du being controlled in terms of d squared u is again the second order Poincaré, and d squared u controlled by Laplacian is like the Calderon-Zygmunt, right? I mean, which in the N2 case, of course, I mean, it's much easier. One can check by integration by parts. So it's a combination of Sobolev-Poincaré and also Calderon-Zygmunt type estimates. But as opposed to the regular Sobolev type inequalities, the crucial difference over here, and that often makes the analysis significantly harder, is the asymptotics of this constant C. So often, so this alpha, what it does when we apply it in the context of unique continuation is that this alpha expresses the vanishing order of the solution. So in a unique continuation problem, we start with the assumption that the solution vanishes to infinite order. So in the end, you have to let this alpha go to infinity. So what is important is that this constant C over here be stable as alpha is large. So in some sense, this expresses the positivity property of the corresponding operator, and this says that the positivity character is somewhat stable as alpha goes to infinity. I mean, I'm just iterating the same words, but in a different way. But I guess.
May I ask a question?
Yeah, sure.
So what is the role of n here?
No, n is like, it's a dimension. So it's an operator in Rn.
Okay.
And what I have written is also wrong in a way. It depends on what, so the C can depend on L as well, the operator, and it better depend on the operator, as we will see in the latest slides. Because earlier what I had done is that instead of L, I had kept Laplacian, in which case, I mean, Laplacian has a very universal definition. So the C should have dependent on N. But the way I have written it, and that is what appears in Aronszajn, Krzyzewski, and Sarsky, the constant better depend on L. And not only L, it depends on the Lipschitz character of the principal part in a very substantive way. Now, I should also mention that from a historical perspective, this is called a Kaleman estimate because Kaleman had earlier obtained an estimate in 1939 itself. So Aronszajn, Krzyzewski, Sarsky is the 1961. In fact, prior to that, there is an earlier paper of Aronszajn which deals with more smoother coefficients, but the one with Lipschitz was the work of, and that it turns out to be quite critical, and it requires a very different analysis, is the work of Aronszajn, Krzyzewski, and Sarsky. And I'll tell you in a while as to why this is more delicate. So what I was saying is that when you have Laplacian U plus VU equals to 0 in dimension 2, okay? So Kaleman had earlier established the strong unique continuation property by establishing a similar estimate in dimension 2. And that crucially exploits the precise eigenfunctions that we know for del theta square, right? Which is like sine k theta cosine e to the I k theta, right? So those are precisely the eigenfunctions, and then it also uses the quadratic nature of the spectral gap in a very crucial way. So using that, he was able to invert this Laplacian in dimension 2, and he could generate an inequality of this type. Because as I said, to prove the positivity is almost equivalent to inverting the operator, right? And that is typically what people do in this business. And so this is one thing that I had to say over here. So that's why it's referred to as a Kaleman estimate. And all people mentioned over here so far are Swedish, okay? Starting from Kaleman to Ehrenstein, Brzezinski, Sarsky. And then it turns out, so as I said, that the assumption on the principal part being Lipschitz is very sharp. And I can tell you in a nutshell as to why the analysis changes significantly from C2 coefficients to Lipschitz. So there are other theories where it's a technical extension and the God is really not in the details, but definitely not in unique continuation problem, where there is a certain subtlety which is involved. So for people who are familiar with some bit of Riemannian geometry, so one would understand that typically when you're dealing with these operators, you can think of it as a Laplace-Beltrami, where the metric in some sense up to some modulo some conformal change is described by this principal part A, right? So if I think of this A as or a modified A as the metric, so this operator can be thought of as the Laplace-Beltrami, right? So let's for a moment assume that we don't have lower order terms, but they are also very easy to generate and one can get rid of. I mean, provided they're bounded or have some smooth, or if they have some smoothness properties by some very basic conformal change. Okay, so this is one thing. So and in any case, the principal part is the commanding part. So the whole thing rests on the principal part, at least at this point. And when we are dealing with these subcritical perturbations. So if you think of this L as a Laplace-Beltrami on a manifold, okay, so the most natural thing to do is to expand them in geodesic coordinates, right? So that would be the most natural thing to do. So now, how to generate the geodesic coordinates? So when we get the existence of geodesic coordinates, it's about solving an ODE, right? And the ODEs involve the Christoffel symbols, right? And the Christoffel symbols are the first derivatives of the metric, okay? So now we know that, and that means that if we assume A to be C2, then the Christoffel symbols, which is the right-hand side in the existence of ODE, is C1, right? So therefore, I mean, the existence is not a problem in that setting. However, if we assume that the coefficients are Lipschitz, then qualitatively, the Christoffel symbols are only bounded and measurable. So even if we approximate these PD by smooth ones, the size of the geodesic coordinates can shrink as we pass to the limit. So this is the principal reason as to why the analysis changes substantially when you pass from C2 to C1 or Lipschitz coefficients. So this is one of the reasons, and that's why it involves a tool from geometric measure theory, which these people were experts on, which is the technique of radial deformation. Anyway, I will not talk about it. So this is just for an historical account. Now it turns out that if one uses more refined estimates, one can even treat unbounded lower order terms. And there are in fact subsequent results for different scaling critical lower order terms that I will also discuss in more details later on. And some of these very prominent results are due to Jerison Koenig, Yifei Pan, Koch Tataru, and so on. So I will be touching about some of these results later in the slide because this is relevant to the content of this talk. Now, a different approach came up in the work of Fred Almgren, who discovered a remarkable monotonicity formula for Q-valued harmonic maps in his study of regularity of mass minimizing currents, which was kind of the next step from studying the theory of minimal surfaces. Now, so if we specialize to the case of Laplacian, the simplest case, what it says is that if you have that U is harmonic in V1, and if we look at this quantity, which is referred to as the Almgren frequency, which is R times the Dirichlet energy divided by the height function, which is the integral of U square over the sphere of radius R, then it turns out that this quantity is monotone increasing as a function of R. And the reason as to why it is called the frequency is because if we assume that U is additionally homogeneous of degree K with respect to Euclidean dilations, then by a standard integration by parts argument and by using the equation, one can show that this frequency is identically equal to k. And now that we know from Fred Almgren that this quantity is for a generic harmonic function is monotone, so in particular, it has a limit as r goes to 0. And this limit captures the degree of the first non-zero harmonic polynomial in the Taylor expansion of U. So therefore, so this is a very natural quantity which will capture the vanishing order, and that is why it turned out that it would be used in the context of unique continuation. So one consequence of the monotonicity of the frequency is that it implies the boundedness of the frequency, and once you have the boundedness of the frequency, it implies the following doubling property. Now, the important feature of this doubling property is that the doubling constant is independent of r as r becomes small. Okay, so say for r less than half. And once you have this, then the PDE is no longer relevant. This implies strong unique continuation. And this is not very difficult to see. So what you do is that you start from B1 and you keep iterating. Okay, so any r is like 1 by 2 to the k, right? So therefore, you know that from this doubling inequality, integral of u square over any b of 1 by 2 to the k will grow like c to the minus k, right? And therefore, any r is like 1 by 2 to the k, right? Because you can always squeeze it between dyadic regions. And then we see that if it is bigger than or equal to c to the minus k times integral of u square over b1, so that is like r to the some alpha, where alpha is the logarithm of this doubling constant, right? By the base change of the logarithm. So, and this is not very surprising because, I mean, in fact, I mean, there is a more underlying general phenomenon over here, which is that, I mean, this constant in some sense expresses the homogeneous dimension that is attached to this measure. And this should be well known to people who work in the abstract theory of metric measure spaces or even hyperbolic graphs and so on. So this constant is attached to the homogeneous dimension, which is attached to this measure, which in this case is integral of u square. And in this case, the homogeneous dimension turns out to be the logarithm of this doubling constant. So once you have that integral of u square is bigger than or equal to r to the sum k, large k, where this k is log of c, then we know that the solution cannot vanish to infinite order at origin, right? So the argument is pretty standard over here. So in 1986, Garofalo and Lin pushed this approach of Almgren further, and they were able to show that solutions to the class of equations that were treated by Aronzine, Krzyzewski, and Sarsky, which has Lipschitz principal part and bounded lower order terms, they satisfy a delicate generalization of Almgren's monotonicity formula. And with that, they were able to show the doubling property. And as I said, that once you have the doubling property, the strong unique continuation follows. So this was one thing. And the other thing that they brought in over here is that they were able to sort of have a more I would say a PD-friendly approach. So their approach is independent of the radial deformation techniques that people use in geometric measure theory. In fact, it was more reliant on relic type identities that shows up in various problems that lie in the crossroad of analysis and geometry, like the Yamabe problem or the prescribed Gaussian curvature problem and so on. So they are related to various existence, non-existence phenomena that people doing semilinear PDs are well familiar with. So they brought in a sort of a different twist to this, the questions concerning unique continuation. And I should mention that in both the works, whether it be of Aronzine, Krzyzewski, and Sarsky or Garofalo, Lin, they had to assume Lipschitz principal part. And it turns out that this is sharp because there is a deep counterexample due to Plish and Miller, where they show that if we assume that the principal part is C alpha for any alpha less than 1, one can always find an example where even the weak unique continuation fails. And I would like to emphasize that these examples are very deep. The reason being, what uniformly elliptic PDs have is the, so to speak, Harnack property, which is the propagation of positivity. Okay. So if we were to produce a counterexample to say weak unique continuation, it means that U is 0 on a non-empty open subset, but it's not 0 in the whole connected component. So that means that the boundary of the 0 set has to intersect the interior. So if we take a point on the boundary of the 0 set, then in any neighborhood, any neighborhood of the boundary of the 0 set, U has to be both positive or negative, because otherwise by Harnack, the positivity or the negativity would spread, and then that point would fail to be the boundary of the 0 set. Now, the thing is that you see, like, it's even hard to find a function which does that. And now we have to find a solution to an equation. So that cannot be easier, right? So this just says that even if unique continuation fails, one cannot come up with very simple examples. Now, there are also extensions to parabolic operators, and this is an aspect I will describe in a lot more details because that's the title of the talk, right? And it is very rich. So there are works of Poon, Escariaga, Fernandez, Vesela, Koch, Tataru, and so on. And there are different versions of unique continuation over here because you can have propagation of the zeros in space as well as the propagation of zeros in space and time. So one is more of a local phenomenon, as we will see, and the other is reliant on global assumptions. Now, I'll just briefly mention applications of unique continuation. So a unique continuation property in combination with the celebrated theorem of Relic implies absence of eigenvalues for the corresponding operators in unbounded domains. So of course, we know that if we take a bounded domain, I mean, we have the Sobolev of compactness, so you can invert the operator. I mean, if it's a nicely positive uniformly elliptic operator, so you have a spectrum of Dirichlet eigenvalues, right? But this doesn't happen if you are in an unbounded domain generically, right? So if you over here, an example to think would be the complement of a ball. Okay, so you cannot find me a function which is an eigenfunction and lives in the right energy space. And over here, unique continuation plays a very pervasive role. And this is something I would not touch upon, right? And Professor Krishna Madali in the audience would be very much would know a lot better than I do, at least over here. But this is a very beautiful theorem to be taught in a typical PD course. Now, there are also quantitative versions of unique continuation. So what unique continuation asks for is that can a solution vanish to infinite order? So once you have settled the question of unique continuation, then you ask the next question, what is the maximum order of vanishing? And over here, there is a very well-known result of Donnelly and Pfefferman, which says that if you take an eigenfunction of a Laplace-Beltrami on a manifold, then the vanishing order of the eigenfunction near the zero set is like square root of lambda. So that is asymptotically the maximum number of derivatives that can vanish. And using this, in the case of real analytic manifold, along with a trick which algebraic geometers refer to, or complex geometers refer to as the resolution of singularities, which is about complexification. You complexify the space in the real analytic case, and coupled with this vanishing order information, they were able to show that the surface measure of the zero set also grows like square root of lambda. Now, it turns out that getting a similar result for smooth manifolds is substantially difficult, right? And there has been some very significant developments in recent times in this direction due to a very young guy named Logunov and his collaborators. So that's also a very interesting subject. Now, it turns out that unique continuation for parabolic operators also yield conditional regularity for fluid flows such as the Navier-Stokes. And over here, there is a very seminal work of Escariaga, Seregin, and Spera, who showed that if you use the backward uniqueness properties for parabolic operators, then what it implies is that if you take a solution to the Navier-Stokes, which belongs to the critical endpoint Prodi-Serine class, then the solution turns out to be smooth. And of course, the Navier-Stokes problem is that whether you can reach up to that, whether you can even assert that the solution belongs to that function space, provided you have that the initial datum is nice and so on. Because I mean, Navier-Stokes is not an equation; it's a supercritical equation. So you don't expect regularity to happen just from nowhere. But when, say, you are in a well-posed or not, we don't even know whether it's a well-posed. There's a well-posed theory, but provided you have good boundary conditions to begin with. Now, there is another thing, so the unique continuation, it turns out, has major applications to various pre-boundary problems. So this is an aspect which is very close to my heart, but again, this aspect is very technical, so I would not even touch on it. So now, okay, so this is all that I had to say about applications of unique continuation. So now we look at scaling critical lower order terms. Now, in the case of Laplacian plus V, typically when V is bounded, you see, like, you rescale, and what you see is that the Laplacian is the more commanding part. But it really depends on what norm you are measuring, the subcritical, the lower order term, which in this case is V, the potential. And it is not hard to see that the scaling critical class for a second order operator in the class of LP is ln by 2. And the reason is, and the other scaling critical class is when B satisfies the Hardy type growth assumption. And this is seen by scaling. You zoom in and then you realize that the norm cannot be, so the norm doesn't get better provided you cross this threshold, which is ln by 2. So the thing is that, so I'll probably skip any further description of it. So when you zoom in, the PD doesn't improve any further. So that is this class ln by 2. And likewise, the same happens for the Hardy type growth assumption. And we see that these are like different function classes, because if I take just even like 1 by mod x squared, it's not in ln by 2. So a unique continuation result for ln by 2 would not imply one for the Hardy type growth assumption and vice versa. Now, when B is in ln by 2, as I have previously said, it's a celebrated result due to Jerison and Kenning, which who were able to show that strong unique continuation holds. And for Hardy type growth assumption, such a result is due to E5 Pal. Now, there are also other scaling critical classes, such as the Pfefferman form class. Okay, when you measure it in a different norm, and there the strong unique continuation is due to one of our countrymen, Professor Sagun Chanilo, along with Alex Sawyer. Now, if I take example like e to the minus 1 by mod x to the epsilon, then it shows that these results are sharp. Because if I apply the operator to it, I see that the potential grows like 1 by mod x squared plus epsilon. You see, so the thing is that if it is more than Hardy, then the unique continuation fails. So that is kind of sharp. And if we take the epsilon close enough, we can cover any LQ for Q bigger than n by 2, for Q less than n by 2. So all these results, they are based on some critical Kaleman estimates, and they rely in a very major way on the spectral gap of the Laplace-Beltrami on the sphere, along with restriction theorems that come from harmonic analysis. Now, strong unique continuation for parabolic equations. So there are various versions of unique continuation in the parabolic case, as we will see now. So if we have that U solves globally an equation of the type LU equals to VU, where L is now modeled on the heat operator, and if the solution has some growth assumptions at infinity that it doesn't grow more than exponentially, and if U vanishes to infinite order at any point, then U is identically 0 for all times less than equal to that. So this is referred to as the backward unique continuation, and this was first proved in this generality by Poon in 1996 by establishing monotonicity for a parabolic version of Almgren's frequency. And now there is an example. Now the next question is that how important the growth assumption at infinity is, and it turns out that it is important because there is a beautiful example due to Frank Jones of a caloric function that is a solution to the heat equation, which is supported in a time strip. And so therefore it shows that if we take a point above that time, we see that over there U is 0, so hence U vanishes to infinite order, but the 0 set doesn't spread. So the growth assumptions are also are in some sense required. Now the other thing that follows from Frank Jones' very illuminating example is that in general, if a function vanishes to infinite, if a solution to a parabolic equation vanishes to infinite order, one can only spread the 0 set in space, but not necessarily in time, right? As one can see in this example, because if we take it a point above that time, there if the solution vanishes to infinite order, then of course the 0 set has spread in space, but all I said is that it will not propagate backward in time. So the best that one can expect for a local solution is only space-like propagation of the 0 set. So such space-like strong unique continuation for local solutions where the 0 set, where you assume that if the solution vanishes to infinite order in space-time, then the 0 set spread, whether the 0 set spreads in space or not. So space-like strong unique continuation in that scenario was established first by Escarias and Fernandez with similar structural assumptions that Garofalo and Lin had, using the so-called parabolic Kaleman estimates. There are also related results on quantitative uniqueness, which is to do with the doubling property and so on, but those are like conditional doubling properties because the parabolic situation is somewhat very different from that of the elliptic case, and they are due to Escarias, Fernandez, and Vesela. And also there are further results for unbounded critical lower order perturbations, which are parallel to the ones obtained by Koenig and Jerison in the elliptic case, and those are due to Koch and Tatarov. Now, there is another variant of unique continuation, which is again space-time propagation, but which is as follows. So if we have, say, U, which solves the PD like this, And if U vanishes to infinite order in the following sense. So over here, you see that in space, you take the ball of size R where R goes to 0, but you sort of average it over time. So this is like space-like vanishing, which is averaged over time. So in this scenario, what Vesela showed is that U is identically 0, both in space and time. So this is another kind of unique continuation. So the result, and this is not just Escaria's, there's also a further result of Escaria and Vesela, which improves upon the earlier result of Vesela. But all these results, they cover potentials which have subcritical growth of this type. So here the epsilon has to be strictly bigger than 0. So recently in a joint work with Nicola and Ramesh, and that is kind of what this talk is meant to be about, we could extend such a result to the scaling critical Hardy case, that is when epsilon equals to 0. So our result can be regarded as the parabolic generalization of the one due to E5 path. So our result can be stated as follows. So we take a stationary, we take a parabolic equation where you have that the potential V has Hardy type growth assumption. And if U vanishes to infinite order in this space-like sense, I'm sorry, I just wanted to mean that in the sense that, you have the vanishing, which is kind of averaged in time, then in this case, U is identically 0. So it's just something that I already described in the previous slide, but okay, so I just stated this as a theorem. So the key ingredients, I'll just outline the proof a bit. So the key ingredient in our work is this critical Kalaman estimate, as we have over here. So you see that this is called critical because this operator, with respect to the parabolic dilations, which is like R in space and R squared in time, this is an order 2 operator, right? So the gap between the homogeneity of U and this operator will be 2, right? So when you square it, it becomes 4. And that is what precisely gets reflected in the estimate. So here we can accommodate more singularity in the weight, which is up to -4, and here you have -2 alpha. So that is why it is a critical weight, because the typical estimates, if it's meant to be subcritical, you cannot go all the way up to 4. So this is one thing. And then I'll make a few comments. So the first term over here, where you can go up to -4, is the critical term in the Kalaman estimate. And the second term is the subcritical term, which has this coefficient alpha cube. You see that because there is a plus epsilon. But you really cannot compare these two terms. Why? Because you have a larger coefficient of alpha, right? A larger power of alpha as a coefficient. So, and it turns out that in the parabolic case, both these terms are important. So in the elliptic case, this term has no relevance. In the parabolic case, this is important. So, so this is the new feature of the estimate. So, okay, maybe a few comments. The first term, as I said, is the scaling critical term, which absorbs the Hardy contribution that comes from the estimate, from the equation. And the second term is a subcritical term. And because of this, because we are in the parabolic setting, it turns out to be relevant. And similar to the elliptic case, the proof utilizes the spectral gap on the Laplace-Beltrami on the sphere in a very, very crucial way. So the proof is somewhat technical because it combines a critical and a subcritical estimate and uses various things. So I would not even touch upon the proof at all. And it would probably not be very inspiring for a colloquium, but rather I will describe how you get the unique continuation from the Kalaman estimate. So that may be of some interest. And moreover, that would also demonstrate as to why we need this additional subcritical term. So I should mention that in the elliptic case, if we just had this weight, that would have sufficed, that would be enough. And I will show you why. But in the parabolic case, we need this additional e to the 2 alpha mod x to the epsilon. This is exactly the new term in the weight that allows us to generate this subcritical term with coefficient alpha cube. And we will see that this alpha cube is more or less sharp. And this plays a very pervasive role in deriving the unique continuation from the Kalaman estimate. Okay, so in the elliptic case, so just going back to the estimate, in the elliptic case, this part is not important. Okay, in the work of Ifai Pan. In fact, I mean, what Ifai Pan used is that he used the estimate that came from the work of Ambren, Georgescu, and collaborators. Okay, so and he was able to apply it to the Hardy case, but in this case, we had to derive this estimate. So this term is not present in the elliptic case. And it's because of this additional weight, and that makes even deriving this estimate somewhat more, somewhat more delicate, because the thing is that when you have this additional weight, when you look at the corresponding conjugate operators, you have further lower order terms, and then with different powers of alpha, and so on and so forth. So the thing is that the spectral gap has to be combined with a very delicate subcritical estimate. So that is really the new feature of the work. Okay, so this is one thing. Okay, so I think I have more or less said what I had to say. Now, let me just give you a brief description of the proof in the elliptic case. So, Kumarjit, before I proceed further, so can you say how much time do I have? So, can everybody hear me? Because Kumarjit...
Just a minute.
Yes.
So roughly
20 minutes. Okay. I think I will be done before that. Okay. So just wanted to know. So proof in the elliptic case. So what we do is that we apply the Kalaman estimate to u times phi. Now the integrability is not an issue because we are assuming that u vanishes to infinite order, right, at the origin. So that means that near zero, even mod x to a large negative power is not integrable, but that is sort of compensated by the fact that u has enough decay. So by a limiting argument, one can put u times phi in the Kalaman estimate. So if we apply it to u times phi, where phi is a cutoff in space, that is, of course, because we are in the elliptic case, phi is 1 in B1 and it says 0 outside B2, this is what we get, right? So when we apply the operator to u times phi, so one part is you take the whole Laplacian to u and keep the phi separate, and then these are the different terms that we get, right? Now, we know that u is the solution of the differential inequality, right? Because we are in the Hardy case. So we put this over here. So when we take the Laplacian u square, this becomes mod x to the power 4, right? So this becomes mod x to the minus 2 alpha minus 4. But then we can absorb this first term on the left-hand side. Why? Because the C is uniform with respect to alpha. Now my alpha is my friend, right? I can take a large enough alpha, so I can absorb the first term on the left-hand side. Okay, so that's good. And so we obtain by, okay, we have, what did I write? So I think this is wrong. Okay, so this should be minus 2 alpha minus 4. And quite honestly, now I realize that I did modify the slides, but the slides that I'm using is not the one that I think I'm using a different text file or a PDF file. So anyway, so this should be mod x to the minus 2 alpha minus 4. I did correct it, but it didn't reflect in the one that it's meant to. So minus 2 alpha minus 4. So I'm very sorry. So let me just see whether which one, does it even cover everything that is meant to. I'm sorry. So what I will do is that I will switch to a different one. Okay. So because I think I'm using a wrong one, and that is the cause of the problem. So presentation. Okay, perfect. So this has now 77. So this is a better one. I'm very sorry for the goof up. Okay. So I'll just quickly go to wherever I have to. So in fact, I could even tell you. So let me just go back for a moment and tell you why ln by 2 is critical. Okay, because this is all written down. So this is seen as follows. As I said, you zoom in, right? So whatever was happening in size R, you make it size 1. So this is how you zoom in near origin. The translation is very irrelevant. Okay, that doesn't significantly change the structural assumptions of the LQ now. So so then we notice that Laplacian of UR is equals to B tilde times UR of X, where B tilde is R square VR of X, right? So this kind of shows that if V is bounded, then V tilde is as small as you want, right? So you really see the commanding nature of the second order term. However, it really depends in what norm you are measuring, right? Because the thing is that if we change variable, we see that the LQ norm of B tilde is equal to R to the 2 minus N by Q, V of LQ over R, right? Because even though, because what may happen is that the infinities would shrink down because of this R square, but the region of infinities may enlarge, right? So there is a kind of competition between the two. And that is what is expressed by this change of variable, right? So we see that everything is good. Finally, we are interested in small n of R, right? Because unique continuation is a local problem. We just want a propagation of zeros close by or in a small enough set. But then we see that everything is nice provided 2 is winning over n by q, which is the same as having that q is bigger than equal to n by 2. So this ensures that the norm of B tilde doesn't blow up as R goes to 0. And likewise, I mean, this is also the Hardy case also one can check the same thing. Okay, so the R square and R square from the bottom and top, they kill one another. So anyway, so this was one thing that I should have mentioned, which I never mentioned. So because I was using the wrong one, okay, wrong slide. Okay. So, okay, so this is now perfect. So now you see, so Kumarjit, is it okay? Now I have corrected this goof up. Maybe I lost 5 minutes, but this is the file I should have used. So now this is -2 alpha -4. Now alpha is my friend, right? Alpha can be as large, so I can absorb the first term on the left-hand side. Okay, good. Now for alpha large, after absorbing the first term, now what we do is that we observe that the other two terms, which have the derivatives of phi, the one has two derivatives of phi, the other has one derivative of phi, they only live in the region b2 minus b1, right? That is where the integrals live. So in that region, what we can do is that we can majorize the weight. And the weight is, because the weight is kind of decaying in mod x, so the weight is majorized when mod x equals to 1, right? So we do that. And what we do is that the left-hand side, we minorize the weight. So we first minorize this integral on the left-hand side after we absorb this term over b1 by 2. And on that set, we minorize the weight. So when we minorize the weight, what we get is 1 by 2 to the power -2 alpha minus 4. So that becomes 2 to the, it should be 2 alpha plus 4, but okay, it is what it is, okay? So it should be, so this should be 2 alpha plus 4 and then with the alpha square. So we minorize the weight over here, we just evaluate the weight at mod x equals to half, and here we majorize the weight. So this is what we get. And now we see that now everything is fine, right? Now you let alpha go to infinity, that being your friend, and we conclude that. Or what you do is that to make it more rigorous, you divide both sides by alpha squared times 2 alpha plus 4, and then you let alpha go to infinity. And then you see that the integral of u is identically 0 in b1 half, and in this way we can keep spreading the 0 set. So these subcritical terms, which involves the Laplacian of phi square u square, and this one, these are not problematic. These are quite harmless terms because they live outside a small region where the weights are not that singular. Okay. So now we try to repeat this argument in the parabolic case. In this case, what we do is that we have to take a cutoff in space as well as a cutoff in time, because that is only an admissible function for the Kalman estimate, right? So they have to be compactly supported in space and time. So what we do is that phi is the regular cutoff in space and eta is the cutoff in time. So what we assume is that eta is 1 for mod t less than equal to half and is 0 outside t bigger than 3 by 4. Okay. And then what we do is that we apply the parabolic Kalman estimate to V. So when we do that, this is the nature of the various expressions that appears, right? And this new term that appears is u square phi square eta t square, because we also have to take del t of eta. There is no del t of phi because phi is only space-like, so it's only this eta. So this is how we take the cutoff. It's a product of cutoff in space as well as and multiplied with a cutoff in time. Okay, good. So now for the first term, similar to the elliptic case, we apply the differential inequality, right? So similar to the elliptic case, when we apply the differential inequality, this becomes constant by mod x square whole square times u square phi square this square, that becomes mod x square minus 4. So that becomes -2 alpha minus 4. And now since alpha is our friend, we can absorb this term on the left-hand side. In the elliptic case, you had alpha square, but in the parabolic case, I mean, for a very delicate technical reason, I cannot even explain as to why we have to cut down, we have to be less ambitious on the power of alpha, but it's enough to absorb this critical term that comes from the Hardy contribution. So the differential inequality part is settled, okay? And likewise, the space-like terms, which involve the first derivative of phi or the second derivative of phi, they are handled similarly as in the elliptic case. So there is some technicality involved over here, but it is kind of believable, right? Because these are things which live slightly far away. Okay, so these are integrals which lives only outside B1. So this weight is controlled. So that's not a problem. Good. So now the only tricky thing is that what about eta t square? Because this can live very close to the origin, right? So how do we sort of absorb it? So this is where the last term, which is u square phi square eta t square, okay, with this weight, this is where the role of the subcritical term comes. And the precise nature of this coefficient, which is alpha cube, as we will see now. So the subcritical term, I've already said many times, is used to absorb this time-like integral, which is the derivative of the cutoff in time. And this is the new feature in the parabolic case. This is done as follows. So what we do is that we judiciously choose our eta so that it behaves like e to the minus 1 by t square near half, okay? In this way. So I'm just thinking of 1 by 2 as the origin because I don't want to shift. Okay. And likewise, it is kind of symmetric. So it behaves the same way near minus half also. Good. So what we do is that So therefore, in the if this happens, then we see that eta of t behaves like 1 by t to the 4 times this exponential, right? So eta t by eta behaves like 1 by t to the 4. Okay, good. So I'm just pretending as half to be 0. Okay, and therefore we just have to look at the region where this subcritical term is dominated by this term. In this region, what we necessarily would have is that alpha cube by x cube, right, or whatever x power, behaves like eta t square by eta. So what we do is that we write it as eta t square by eta square times eta square. Okay, so the eta square being the same. So eta t square by eta square behaves like 1 by t to the 8. So you see that alpha cube by mod x to some power has to behave like 1 by t to the 8. So the power, okay, so what is important is the power of alpha, not really the power of mod x, as we will see. So any little good power of mod x would do. Okay, so just think of mod x to be 1. So what we need is that alpha cube has to behave like 1 by t to the 8. Okay, so that means that eta of t in that region, wherever this time-like integral on the right-hand side dominates over this subcritical term, eta of t has to behave like e to the minus alpha n by 8. Why? Because the eta of t had like e to the minus 1 by t cube. So alpha cube is like 1 by t to the 8. So 1 by t cube is like alpha to the 3 by 8 into 3. So that is alpha to the 9 by 8. But now the important thing being 9 by 8 is bigger than 1. And this becomes my friend. So then what we do is that I should have done it before. Eta of t square is like eta square times eta t by t eta whole square. By writing it this way, we notice that this integrand over here on the right hand side, which is our enemy, can be broken down in this manner. So we write this eta square as eta times eta. Okay, good. So that one eta appears here, the other. So then in this region, as we said, that the eta t by eta. So this is eta times eta t by eta whole square. But eta t by eta, as we previously had, behaves like 1 by t to the 4. So eta t by eta square behaves like 1 by t to the 8. Okay, good. And then what we do is that we express everything in terms, we just exponentiate this whole thing. Okay, so this is how we express it. So mod x to the minus 2 alpha is like e to the minus 2 alpha mod x, and this 1 by t to the 8, as we had in our analysis, 1 by t to the 8 behaves like 1 by t to the 8 behaves like alpha cube by mod x cube, which in particular implies that eta of t, which has this power, behaves like e to the minus alpha 9 by 8, right? So that is important, by mod x to some power. That power, as I said, is not really significant. So then what happens? Then this eta, so there is one eta, which is fine. The other eta has like e to the minus 1 by t cube, right? So that is like e to the minus alpha 9 by 8 by mod x to the 9 by 8, right? Because I'm only concentrating on the region where the subcritical term is dominated by the right-hand side. So this is how the behavior would be in that region. And now we see that we are in a very good shape. Why? Because one is that log of mod x minus of log of mod x would drag this term to plus infinity, but minus of 1 by mod x to the 9 by 8 will drag this term, this exponential, with this exponential would drag it to minus infinity, right? So this is more dominant over this term and when mod x is small, right? So this term dominates. And now, of course, you also need a favorable power of alpha, and that one is because here you have a power of alpha, which is 9 by 8, which is dominant over alpha. Good. So therefore, if we take mod x small enough, then this term can be morally dominated by 1. So this whole integral, this bad integral, can be dominated by integral of u square. And once you have removed the weight, it becomes a subcritical term, then one can repeat the argument as in the elliptic case. So now one may wonder that we have made this precise choice of eta. So one can try that. If you play around with your choice of eta, that you can make it exponentially decay like any power, you see that you will have very little room, because what happens is that from that analysis, one would realize that no matter how much you try, okay, the coefficient of alpha in the subcritical terms has to be firstly bigger than 2. And in fact, by playing around with the powers, you will see that it's very close to 3. So you have very little room over there, because it has to be tight from both ends. Because you need enough power over here so that you are able to manufacture this power over here, which is bigger than 1. Okay, I mean, this is a numeric, but unfortunately, I mean, in this, in the context of unique continuation, when it comes to critical lower order terms, the God is indeed in the details. So this is all that I had to say. Okay, and it remains to be seen whether we could control this term. So it remains to be seen whether our result can be extended to parabolic operators with variable coefficient principal part. But most of our analysis uses the spectral graph in a very crucial way. So it's not very clear at this moment to what extent we can sort of push our regularity assumptions on the principal part. So this is the technical question that needs to be tried. And this is the paper that we had. And with this, I would like to end my talk. And thank you all for your kind attention. This is the most important thing that I have to say. So, Kumarjit, I'm done.
Thank you very much for a very engaging talk and questions, comments.
So I should open the Zoom thing first. Okay.
Yeah, maybe you can stop screen sharing.
Okay, perfect. So now I can see everybody. Okay.
You know, I always felt for a long time that the unique continuation kind of results will somehow contribute to solving the Riemann hypothesis. So do you have have you ever thought about anything like that?
No, I haven't thought even nearly that far, right? I mean, it would be a very dishonest answer to say that I've been thinking anything on that front.
No, but did you ever think of Riemann hypothesis? And then, because, yeah.
So yeah, generically, I would say that, I mean, it was your courses as well as Professor Keshavan's courses that triggered at least the interest of some of us in analysis. And then it was kind of different from the theme of education that typically